Now we've talked about entering the basic frames and how to give the joints restraints and constraints, and then how to create load cases and load combinations and all that. And it seems that we are now ready to run the model. But there's one thing we haven't talked about, and we need to talk about that first, and that is shells. Now we know that no analysis model is really complete without shells. Maybe not that much in steel, but especially with concrete structures, we have to model a lot of times our shear walls and our slabs, etc., using shells. And so I need to tell you about the various features we have in Comosys regarding shells. Now, the first thing which I need to tell you is that in Comosys, you don't enter shells directly, but what you do enter is something we call supershells. And supershell is based, so I'm going to enter a supershell. And what you do is you simply go around the entire floor, for example. So let's let this be the entire floor. And the supershell appears in front of you. Now, if you double click on that, you open the dialog box of the supershell. And here you can change how it will be drawn. So I like the contoured solid. There's the thickness of the supershell, 200 millimeters at the moment. There is a uniform density of because the supershell is going to be meshed for the analysis. So right now it's about 1 meter. And there's a default material which we have, and we can change that to any other material. For example, I can go down and I can convert it into, say, a C35 concrete. 200 millimeter thickness, and say apply. Okay, and now we have entered the properties of this supershell. If we were interested in how this is going to be meshed, then all we need to do is just press this button. This is like a default preview, a preview of how the mesh is going to come out. And if we do that, you will see that this is what the mesh is going to look like. One thing I want to say at this point is that these beams you see over here, because the supershell will be meshed like this at these points, for the finite stiffness matrix assembly, this beam will also be broken into little parts in the background. You won't notice that, but in the background, while it's assembling the stiffness matrix, in order to have a continuity in the displacements, these beams, wherever they're touching the supershells, they will be broken down into their own subparts. Now, these supershells have some really amazing features which really make your life easy when it comes to the analysis of shells. And one of them is its ability to sniff out or locate whenever there's a frame element touching it. So I already talked about how these will be meshed because the supershell is in contact with it. But this is not only at the edges. If I were to, for example, enter a beam like that and say dx 1000 using this direct entry method, and at the other edge, if I were to say dx minus 1000 and basically enter the inclined beam like that, and now if I ask the program to give me a preview of the mesh, you will see that now the mesh has changed and it's going along this line of the beam. And this, not only will this beam be broken down into subparts, but the mesh created by the supershell is also in perfect union in perfect harmony with that particular frame element. But that's not all. Let's say we were not happy with this density of 1000 which we see on the screen. Let's say we wanted a higher density, but the problem was that, so for example, we could just make the density higher. We can call it, say, 300. And when we do that and do the mesh again, we can see that the density has been changed, and once again it also fits the beam along that line as well. But this is not what we want to do. What we want is to keep that density of 1000. Let's keep it back to the normal number. And but we know that for some reason there's a stress concentration in this area, and we want to have a higher density, but only around this point and not on the entire slab. So what we do is we go to our mesh modifiers and we say I want an internal point at this point. That's the first thing we do. And the next thing we do is we want an internal mesh density at that point. And we put that element over there as well. And then we can just select them and press enter. And for the density point, what we can do is we can say we want a density of say 250 at that point. And if this number is, whatever this number is, this number should be about 3 times that number. So let's call it 750. This is the radius around which it will spread out. And once I do that, and then I press this preview mesh again, you will see that the density has been reduced around that point only, and it slowly grows back into this normal number of 1000, which we had elsewhere in the supershell. But it's not just internal points which we can have to modify the density of the broader region. We can also have internal lines. So I could go to the mesh modifiers and say I want a mesh internal line between, say, this point and this point. And then I can say I also want to change the density along that line. So I can once again select the same 2 points. And once I do that, then I can select those objects like that, go to my density line object, double click on that, and give it a density of, say, once again 350 millimeters, and give this one a higher number because this is a line now, not a point. And once we do that and we do the preview mesh again, we see that not only do we have this increasing mesh size around the point which meets up with this 1000 general density, but we also have the same phenomena going on around this line, and it's meeting up with the broader density of the flag of the slab as it goes out into the outer regions. But even that is not all. Slabs and walls, you know, they can have holes in them, right? And what if this supershell had a hole in it? How would the meshing algorithm behave according to that? So you can go to your cut commands, for example. So what you can do is you can go to your polygon cut, select this supershell, and say I want to cut this. I want to make a rectangular opening in there, and you just select the points, and the rectangular opening is created. And the moment that happens, your mesh basically regenerates. And if we were to select that cut and move it around, so let's right click and say move linear and give it, let's say, okay, any number in the y direction, and say move, you can see that the mesh is adapting as the cut is moving, even as it is going through that density line. It's very convenient. Let me just remove the cut, and you can see even the density is still being applied along that line, and the cut is being made. And basically all our requirements which we wanted a hole in this area, we wanted the line density to increase along this line, but we wanted the general density to be 1000. All those requirements are being satisfied. Now we know that the supershells are intelligent. We've seen that, and they can sniff out these elements which are lying in the plane of the supershell and mesh according to their presence. But what if these frame elements were not in the plane but were actually outside the plane in the direction, let's say, perpendicular to the plane? So let's say we had a column sitting at this point on that slab and another one sitting at this point. Now these are not inside that plane, so let's make a beam on top of it as well. And let's make matters even worse, and let's go to the analysis tab and create a new supershell, which is like a shear wall, or like a wall, let's say. And let's create it like that, and let's double click on it. Let's change the color just for convenience, and make the settings, turn it into a concrete element, and let's give it let's say a different density of 350. Now we have a different, even more complicated situation in which we've got some elements coming up vertical or perpendicular to this existing supershell, and one of them is a supershell itself, and they're also frame elements like you see on the screen. What will it and the density of this particular supershell is 350, while the overall density of this one is 1000. So what's going to happen at these points of contact? So let's go and ask the program to do the preview mesh for us. And when we do that, we see that this one has been meshed with 350, and as it touches this one is, because the density is higher, it's being forced to adapt to that one. And on the back side as well, you see a perfect harmony between the meshes. And if we were to convert this into line mode, you will see that the columns are landing at a point which is an exact node point for the supershells. So what we have is exactly what we would have done by hand. This would have taken us hours to do. And you can probably already feel the kind of things, the kind of advantages this supershell meshing is going to give you. Those who are thinking about steel might already be thinking how they can use these features to design or analyze steel connections, if you will, to a certain extent. And especially for concrete structures, you've already seen the kind of power it can give. If we wanted to make a shear wall over here, we could just enter a supershell again. Once again, as you know, we don't enter shells, we enter supershells in Comosys, and Comosys does the rest. So we can enter a supershell, change the settings if you want to, whatever. And then if you wanted this bottom part to be restrained, we could assign the line support, for example, and we could just say from here to here there is a restraint. And what that will do, what that will tell Comosys is, if you double click on that, once again, just like the joint restraints, we can have ux, uy, uz, rx, ry, rz, constrained or unconstrained. You can remove those. But what it will tell Comosys is that when you're doing the analysis, this is going to be meshed, obviously, this wall. And so some of those joints will come along this line, on this line. So whatever joint ends up on this line, that needs to be fixed like this, according to these fixities. Similarly, just like the line support, you could have point supports as well. So instead of having the entire line fixed, you could have just a point over here fixed, and then whatever node would come to that point would be fixed by Comosys. Now, sometimes slabs don't have a uniform thickness across the floor. So you could have one thickness, and then you could have a slightly bigger thickness in a particular region, for example. So what you do in Comosys is you go to your shell tools and you have a Supershell region modifiers. And once you select that, you can select the Supershell, right click, and then select the points where you want a different thickness property, for example, or some other stiffness property can also be modified. And once you do that, what it does is, if I were to just say hide this, for example, what it has done is it has created a hole in the original shell, but it has added another shell exactly at that point. And this particular shell now you can modify with a different thickness if you wish. If you just double clicked on that, you can have a lot of thickness. You can change the thickness from there. You can assign it some soil springs. So maybe only this particular part can have some different soil spring, maybe, or some load case related. You can take existing loads from the parent supershell. So a lot of things can be done with these region modifiers, which are very useful. Now, obviously, you can assign loads to these supershells, and if you go to the surface load menu, you can assign the supershell a surface load, which needs to be a uniform load, basically, along the entire supershell. You can also assign a line load, as you can see over here. You can assign a point load, as you see over here. So whenever the mesh will be created, if there will be a node at that point, and the force will be transferred to that node. For the line loads, which you create, for example, when the mesh will be created, there will be an internal line along that. So there will be nodes along this line, and whatever nodes are along this line, they will be these loads will be transferred to those nodes. But more importantly, because these three are common, they're found in most programs. But much more importantly is this loading fields concept, which we have developed in Comosys. And this is really interesting. So let me show you that for a second. Now, most programs have this concept which they call joint patterns. And this is a very difficult concept to utilize. And it's very cumbersome in the real world because your mesh keeps changing. And if you define your joints beforehand and you define the joint pattern beforehand, but then you find out that the mesh wasn't enough or you needed a hole somewhere, then everything needs to be redone. Now, instead of doing that, what we have is these vector fields in Comosys, which you can define. So you can have a linear vector field, and what that means is that you have a linear function it's a vector function in the form of ax plus by plus cz plus d. This is the function, and you can define these a, b, c, d parameters, and you can set the origin of the coordinate system according to which this function will be defined. Or you can have, instead of a linear one, you can have a quadratic distribution, which will be of the form of ax squared plus a1x squared plus a2x plus b1y squared plus b2y plus c1z squared, and basically that quadratic formation. And once again, you can set your parameters according to that. Or you could have an exponential distribution with a different format, or you could have an exponential type 2, which is a slightly different form of the same function. You can have a power function of type 1 and 2. So you have 6 different types of fields which you can have. And then you can also tell the program that although this field can have both negative and positive values, but I want to only use the positive, I only want to use this where the values are positive or 0, or only where the values are negative and 0. And then, since it's a vector field, wherever it runs into the coordinates run into the actual supershell. So this is the supershell at the back, and this orange is the vector field. Wherever it will hit, so whatever the coordinates of the supershell will be, this vector field will have a value because it's a vector field defined at all xyz coordinates. So whatever the xyz coordinates of your supershell are, the vector field will assign a force at that point according to its own value at that point. And this is extremely powerful, so it can be used in silos for the internal loading of the materials, which are usually not linear functions. There are different kinds of functions are used. And because you have the polynomial option as well, and you have the exponential and the power function option, you can do a lot with this kind of loading. And this is really unique to Comosys, and it will help you solve a lot of your loading problems.